Yeah, so there we go. It's a pleasure to welcome Becky Armstrong from the Universitat Münster, who's going to talk about the uniqueness theorem for twisted groupoid sister algebras. Please, Becky, go ahead.
Thank you. Yeah, so thanks for the introduction and the invitation to speak. So this talk is based on a preprint that I put on arXiv earlier this year called a uniqueness theorem for twisted groupoid C-star algebras. I was told that groupoids come up from time to time in this this seminar, so I will show you the definition of groupoids, but I'll try not to go on and on too much about them. And then I'll talk about twists. So there's two different ways that people commonly, or at least two, people commonly twist groupoid C-star algebras, and I'll talk about both of them. And then I'll get to the construction of twisted groupoid C-star algebras, and then present this uniqueness theorem, and also some applications in the form of simplicity characterizations. Okay, so starting with groupoids. So I guess the nicest kind of definition I can give is that a groupoid is a small category in which every morphism has a unique inverse. So I like to think of a bunch of dots and arrows between them, and for each arrow, you've also got one going in the opposite direction. And another good thing to have in your mind is that a groupoid is a generalization of a group that can have multiple identities, and the multiplication is only partially defined. And so for each of your arrows or your morphisms in your groupoid, gamma, there's the range of gamma, which is given by gamma times gamma inverse, and the source of gamma is gamma inverse times gamma. So we're defining these in terms of the existing like composition or multiplication and inversion.
So you use that convention, yeah.
Yeah, I mean, you could also just say category comes equipped with them, but either it ends up being the same thing. Yeah, and I read composition from right to left as well. Yeah, so we have range and source maps, and then there's a bunch of kind of intuitive axioms that the multiplication and the inversion satisfy, and you can use these to prove, or you could have just said this by definition, I guess, that the composable pairs are this set G2 of pairs alpha beta, where the source of alpha is the range of beta. So I usually picture these as arrows pointing to the left. So then you've got like alpha times beta. I don't know if this is probably mirrored, so I don't know if my hands are helping. But anyway, the source of alpha connects with the range of beta, and then you combine them to get an alpha beta in your groupoid. Okay, and then there's also this unit space, which I denote by G0. So this is the collection of all possible either ranges or sources of the arrows. It doesn't matter because they go both ways. And these elements behave like identities wherever composition is defined. So it's sort of like the unit of a group, except that composition isn't defined everywhere. So you have to have some different units. Okay, so then to associate a C-star algebra to your groupoid, you want to give your groupoid a topology. So sort of the most general kind of thing people seem to do is that you talk about topological groupoids, which are just groupoids with a topology that makes all the operations continuous, and the unit space is Hausdorff. But for me, my whole groupoid is going to be Hausdorff. I mean, people often like to deal with non-Hausdorff groupoids, but not today. And also the groupoids are going to be étale, which means that the range map, or equivalently the source map, is a local homeomorphism. So it restricts to homeomorphisms of open sets. And this is a nice property because it's the groupoid analog of discreteness for groups. So if you've got an étale groupoid, but it only has one unit, then it's actually a discrete group. So throughout, I'm going to have a second countable, locally compact Hausdorff étale groupoid G, but I'll just call this a Hausdorff étale groupoid for, that's a mouthful. So yeah. Yeah, so I mentioned like people often drop Hausdorffness. They also might drop étaleness. That makes the multiplication of your C-star algebra less nice. Second countability gives you that the C-star algebra is separable. So I don't usually see people dropping that except in the setting of, you can build like algebraic, purely algebraic, kind of like these Steinberg algebras and twisted Steinberg algebras that aren't C-star algebras. In that setting, maybe I mean, people don't usually have second countable for that. But anyway, these are the assumptions that I'll have. And the Hausdorff étale groupoids are nice because they have an open unit space and they admit a Haar system. So anyway, I'm going to go through one quick example just because it'll come up again in a sec. So equivalence relations can be realized as groupoids. So if you take two elements that are related in your equivalence relation, and whenever you do have these two elements that are related, you draw an arrow between them, you're always going to get an arrow going back in the other direction by symmetry of the relation. So you're going to have inverses. Then if you allow yourself to compose arrows when they sort of link up, so if you think of x, y as an arrow going from y to x, then these arrows link up. And then you compose them by, x, y times y, z is going to be the arrow from z to x. And this is going to be back in your groupoid by transitivity. And then using these formulas from the previous slide, like, so here your xy is your gamma. So range of gamma is gamma times gamma inverse. If you work that out using these formulas, you're just going to get xx. Or we sometimes just say that the range of xy is x, like the head of the arrow. And the source of xy is y. And then the unit space is all the possible ranges. So you can think of that as all the pairs xx, which you could view as loops, or you can just think of the unit space as being x, like the actual points. But anyway, so equivalence relations are an example of a groupoid, but there's all sorts of other examples, like group actions give rise to these transformation groupoids. Sets can be realized as groupoids, because if your groupoid just consists entirely of units, then you can't multiply anything, so you have a set. There's groupoids associated to directed graphs and the topological and higher rank analogues, so topological K-graphs, etc. Anyway,
so
okay,
this,
so
that would be an example of these relations are an example of a graph which has at most one arrow between two vertices, right?
Yeah, well, I guess, yeah, two arrows, like the one pointing the opposite direction as well. But yeah, one arrow from x to y. Yeah. Yep. And one backwards. Okay. So I'm going to define the isotropy on this slide. So to begin with, for each unit x, I'm going to define G superscript x to be the morphisms with range x and G subscript x to be the morphisms with source x. And I mean, this is just notation that people use, but it's not particularly like intuitive if you've never seen it before. I used to just write like G with an upwards arrow, like to remind myself, although now I just know. Anyway, if you intersect these two sets, you get a group, because everything in there has range and source x, so you can compose everything. And there's one unit, which is just x. So we call these isotropy groups. And if your groupoid is étale, then all three of these sets are discrete. So in particular, these isotropy groups are just discrete groups. And then the collection of all the isotropy groups is called the isotropy. So these, if you were thinking about dots and arrows, these are just it's like a bundle of groups, and each of them just consists of loops centered at each of the units. So the unit space is always contained in the isotropy, but then there could be extra elements. Although, yeah, as was just pointed out, not for equivalence relations, you don't have any extra elements. Okay. I mean, you don't have any extra elements that have range and source the same thing. So yeah, so example, equivalence relations, the isotropy is just all the pairs of the form XX, so just the unit space. For a group though, everything in the group is in the isotropy, because everything has range and source equal to the same thing, the single unit that's in the group. And these are the two extremes that can happen. Like you can have your isotropy containing only the units, or you can have your isotropy being the whole groupoid, or you can have something between these two extremes. And okay, so we like to talk about the topological interior of the isotropy of G. We're going to denote this by IG. And also there's going to be an E, a groupoid E that comes in later. So I'll talk about IE as well. And this is quite a nice, this is a subgroupoid of G. It's quite a nice subgroupoid because it inherits G's topological properties as well. So if G is Hausdorff étale, then so is IG. And then also when you're Hausdorff étale, you have an open unit space. So the unit space is going to be contained in the interior of the isotropy. So actually IG and G have the same units. And okay, one more thing that will come up later, and I'll remind you of it later, is that you call your groupoid effective if the interior of the isotropy is just the unit space. So for instance, discrete groups are never effective. Equivalence relations always are. There's no topology, but yeah. Oh, I guess a trivial discrete group would be effective, but that's boring. So yeah, the interior of the isotropy is going to come up a lot in this talk, because not only is it a nice subgroupoid of G, it's also, I mean, you know, I'm studying twisted groupoid C-star algebras, and the C-star algebra associated to the interior of the isotropy is, I mean, it can tell you a lot of information about the bigger twisted groupoid C-star algebra associated to all of G. And so, yeah, so this is why they'll come up. Okay, so what do I mean by, I just use this word twist? Well, there's two different notions that I'm going to talk about of a twist, but I'm going to focus on the more general of these two notions. So I'll start with the less general one. The less general notion of a twist comes from something called a two cocycle, which you might be familiar with from group C-star algebras. So a continuous two cocycle in a topological groupoid is a continuous map that takes a composable pair of groupoid elements and maps it into the complex unit circle. And it satisfies these two conditions. So, I mean, you don't have to, you know, memorize this or anything like that, but this is called the two cocycle identity. And I sort of think of it as like an associativity style condition, where like, if you look at this term here, and you're kind of thinking, well, how can I get this beta into the second coordinate? Is it the same thing? Well, no, it's not, but it is if you adjust by these two terms. And this condition appears in like cohomology of groups. It falls out from the definition of a two cocycle, because the two cocycles are the elements of the kernels of the co-boundary homomorphisms or something like this. And yeah, I mean, if you work out what that means to be in the kernel, then it means that you satisfy this condition. And then we also want two cocycles to satisfy this normalization. Whenever the unit into E, you get one. Okay, so we build this into the construction of our C-star algebra. If you've seen just the usual groupoid C-star algebras before, that will help, or even group algebras or group rings. Or I heard a noise. Is someone trying to ask something, or
no?
No.
Your voice comes and goes. I don't know if it is my internet connection or if it's a general thing.
Okay. I'm sitting as close as possible to my modem and stuff, or whatever it's called. So yeah, I'm sorry about that. I'm on like edgy room.
The public says it's okay. So it might be my connection.
Okay. Yeah, I do sometimes get a bad connection in here. Sorry about that. Yeah, I can repeat things if people need me to. So just call out. Oh, I just noticed the chat. It's fine. Yeah, okay, right. Okay. Yeah, anyway, so you incorporate your sigma into your, no, hang on, I'm getting ahead of myself. Okay, so what I was saying was you start with the vector space of continuous compactly supported functions on G into the complex numbers, and you turn this into a star algebra by defining this multiplication where, so you take your two functions and you want it to map gamma to this sum. So you've sort of decomposed your gamma into all possible decompositions, alpha, beta. You plug your alpha into F and your beta into G. And then you want to twist this by this element of the complex unit circle. So this is, you know, it's going to rotate it, right? And this is, you know, depends on alpha and beta. And I mean, for non-twisted groupoid C-star algebras, you wouldn't have this term here. So you can think of non-twisted groupoid C-star algebras as trivially twisted, in the sense that you've just defined your sigma to always be one. So this makes it clear that twisted groupoid C-star algebras are a more general construction than groupoid C-star algebras. And this is sort of a kind of, I mean, I sometimes forget that this isn't obvious because I'm used to working with these, but I mean, a lot of the time when you introduce an extra adjective in front of some construction, that makes it less general, like a group and then an abelian group. But a twisted groupoid C-star algebra is not a type of groupoid C-star algebra. It's a more general class of C-star algebras. But anyway, yeah, and I mean the étaleness of the groupoid is what makes this sum, converge. And then you define an involution, and that involves the 2 co-cycle as well. And this gives you a star algebra.
So,
and
sorry, the sum converges, or is it finite?
Yeah, sorry, finite. Yeah, I meant finite. I mean, it also converges, I suppose, but it's just finite already. Yeah, because the functions are compactly supported, and you're essentially summing over one of these G superscript X's or something from before that are discrete. So yeah. Oh, and the multiplication is associative because of this 2 co-cycle identity C1. So yeah. Anyway, so then there's 2 norms that people commonly complete this under, and I won't go into detail about them because I'm going to talk about the more general version of these later anyway. But there's a full and a reduced norm, and they give you the full and reduced twisted groupoid C-star algebras, which we denote like this. So the R here is for reduced. And yes, so this is a thing people study. But I'm not going to focus on those ones. I'm going to focus on these more general ones. So, I mean, if you know much about like group cohomology, like one of the kind of important results is that given a 2 co-cycle on a group, you can use it to construct a group extension. I'm just talking about discrete groups here. And you can also take a group extension and use that to construct a 2 co-cycle. And there's a 1-to-1 correspondence between the cohomology classes of 2 co-cycles and the congruence classes, equivalence classes of group extensions. For groupoids, we don't quite have this. So what we do have is that you can use a 2 co-cycle to build some sort of groupoid extension, which I'm going to show you. But you can't always take a groupoid extension and use it to build a 2 co-cycle. So continuity is what breaks. But I'll go into more detail on this. First, I just want to give the definition of these groupoid. G is an exact sequence starting from so G0 cross T, you think of as like a trivial bundle with fibers T. Then there's this injective map into E, which is a groupoid, and a quotient map Q onto G. And the sequence is exact in the following sense. So, okay, I is injective, Q is a quotient map. And then we want some sort of thing like the image of I is the kernel of Q. But when you've got a groupoid map, the kernel means that, in the kernel, if you get sent to a unit, that's how you get killed. And so this is saying that the pre-image of a unit X is precisely I of X cross like anything in T. Okay, and then there's a bunch of other conditions that need to be satisfied. So, okay, as I said, E is a groupoid. It's a locally compact Hausdorff groupoid, and its unit space is just the image under I of G0 cross 1. I and Q are continuous groupoid homomorphisms, and they restrict to homeomorphisms of unit spaces. So I'm going to often probably say that E is like the big groupoid. I'll talk about the big groupoid and the smaller groupoid, because E, there's a projection or a surjection of E onto G, but their unit spaces, I'm going to identify their unit spaces. And also, the image of I is central in E. So, okay, if I take anything in the image of I want it to commute with some epsilon in E, always. But to get the commutativity to work, like when I swap these 2 terms, the unit here changes from the range of epsilon to the source of epsilon, because these are elements of groupoids, so I want the composability to work. Now, the important thing here is that this defines an action of T on E. Okay, so this action will come up a lot. And so, yeah, that's the main thing to take away, is that T acts on E. It's obviously both a left and right action because of the centrality. And what you also have is that, if you have 2 elements of E that map to the same element of G, then in E, they just differ by some element of T. Like you can act on one with T and you'll get the other if they map to the same thing in G. And then you have something topological kind of this nature. E is a locally trivial G bundle in the sense that for each alpha in G, there's an open neighborhood U alpha and a continuous local section back to E. So this P alpha, Q composed with P alpha is the identity. And you can use that continuous local section to define a homeomorphism. So, okay, this is kind of crazy, but what this is saying is that if you look at the pre-image under Q of your set U alpha over here, it just looks like U alpha cross T. And that's because, I mean, so you take, say for like a beta in U alpha, you take whatever representative you like back in E, and then you can just act on it with any Z to get all the other representatives. So you end up getting that, yeah, you get this homeomorphism. And so your E kind of looks locally like G cross T. So it's not globally homeomorphic to G cross T in general, but locally it is. And so sometimes, like you always have these continuous local sections. Sometimes in special cases, you might have a continuous global section, like a section P defined on all of G that's continuous. I mean, you always have such a section because you can just pick out whatever elements you want to send to whatever you want, right? But continuous is the key. And in that case, you'll have the E looks like G cross T. It usually, no.
That would be the trivial extension.
Not necessarily trivial, because I'm only talking about when E is homeomorphic to G cross T, but it might not be like isomorphic, like as a twist.
Okay.
But yeah, it will be also, okay, what it corresponds to is that if you have a continuous global section, you can use it to build a 2 cocycle. So in the case of just when there's a continuous global section around, you do have this one-to-one correspondence between 2 cocycles in groupoid extensions. But in general, the groupoid extensions are like a more general construction than 2 cocycles. I'm going to go more into detail on that. But
so in general, you have something like a local 2 cocycle.
Yeah, I guess so. I mean, I've never seen anyone talk about that. I don't really, I mean, I guess you could define it on U alpha or something. Yeah. Yeah. Although, well, no, because U alpha isn't a groupoid. So then I don't know what, like if you took composable pairs in U alpha and multiplied them, you might kind of exit out of U alpha. And so you might not be able to define a 2 cocycle actually. Yeah.
But I'm sure that there is, I mean, one can invent some notion that describes these local sections all together.
Yeah,
all
like,
together, and
yeah, maybe
something.
Yeah. I mean, if your unit space is totally disconnected, you can use all the local sections to build a global section. So you'll always have one, but I mean, a continuous global section. But yeah. Anyway, so some examples of twists that will come up. If you start with a twist E over G, then you can build this sort of trivial twist where you just look at the pre-image of the unit space, which is precisely, I mean, the image of I is the kernel of Q, right? So this is a trivial twist in the sense that this one actually is just homeomorphic to your groupoid that you're looking at, which in this case is G0 cross T. So, okay, that's kind of a boring example. An important example is that the interior of the isotropy of E is always going to be a twist over the interior of the isotropy of G. And it looks precisely like the pre-image of IG. So, yep. And then this also works for the isotropy groups. So if I take, this is the interior of the isotropy group at X in E, and this is a twist over the corresponding interior of the isotropy group in G. So we're often going to study, as I mentioned, twisted groupoid C-star algebras by looking at the corresponding twisted either isotropy C-star algebras or isotropy group C-star algebras. These are discrete groups. So in that setting, the twists actually always come from 2 cocycles. And this will give us information about the bigger twisted groupoid C-star algebra associated to G and E. So we definitely need to know that the interior of the isotropy is a twist over, like of E over G. Okay, and then this is the example I mentioned before. If you take a 2 cocycle, you can use it to build a twist. So you do it like this. So you take your E, I'm going to call it E sigma because it depends on sigma, as a set to be G cross T, but it's not going to be, so it'll be homeomorphic to G cross T, right? But it's not going to be isomorphic because I'm going to define a different multiplication. So this is what I was getting at before. So the multiplication is the following. So if you take alpha Z times beta W, in the first coordinate, you just multiply if you can, like if alpha and beta are composable, but in the second coordinate, you're going to incorporate the 2 cocycle term. And then similar for the inverse of alpha Z, you're going to have the 2 cocycle appearing. So that's the E that goes in your twist, and then you need an I and a Q. So your I is just going to be inclusion, because remember your E sigma just looks like G cross T. So you just include, and then your Q needs to project onto G. So yeah, it's just the sort of obvious, pick out the first coordinate thing. And then you get a twist. Okay, and I mean, I haven't shown you the construction yet of twisted groupoid C-star algebras from these groupoid extensions. I only showed you the one from 2 cocycles so far. But when you do these 2 constructions of twisted groupoid C-star algebras, you do get the same thing if your twist and your 2 cocycle are, you know, related in this way. Okay, so then for the other direction, so in the case where you've got a continuous global section, as I mentioned, you can use that to build a 2 cocycle. And then once again, you're going to get the same twisted groupoid C-star algebras. So the way you do that is, okay, so say you've got a continuous global section, there's a 2 cocycle, and you sort of define it in this kind of weird way. So what's going on here is that if you look at this term on the left-hand side and you apply Q to it, so Q composed with P is the identity. So you're just going to get alpha beta times alpha beta inverse. So this is a unit. It's of the form gamma gamma inverse. It's the range of alpha actually. But the point is that because Q of this is a unit, this term here on the left-hand side is in the kernel of Q. So it's in the image of I. So it looks like I of something, and your I is injective. So actually there's only one element of T that can go here. And so you just define sigma alpha beta to be whatever that element of T is. Okay, and then it turns out, because of, you know, continuity of everything, that this is a continuous way of defining your sigma. And it turns out it also satisfies like the conditions of being a 2 cocycle. So the 2 cocycle identity, and it's normalized as well. And so this is how you can build a 2 cocycle. And then if you use that 2 cocycle to build a twist, like in the sense of the previous slide, this E sigma that I built, that E sigma that you get is going to be isomorphic to the original E that you started with. And the isomorphism is just, I mean, it's the same as this homeomorphism that I showed you before, coming from the continuous local sections. So you just, if you've got a gamma in G, you just pick a particular representative of your gamma and you can act on it with your Z. And so you get an isomorphism of this twist coming from sigma and the twist that you started with. And so isomorphism here means not only are the groupoids homeomorphic, but also, yeah, the twists are isomorphic, like as twists, in the sense that this diagram commutes. And so this is why I said before that if you have a continuous global section, your E doesn't necessarily look like G cross T. It could look like G cross T, but with this twisted multiplication by sigma. But homeomorphic to G cross T for sure. Okay, so how do you build twisted groupoid C-star algebras from these groupoid extensions? That's what we're going to talk about now. So once again, you start with a vector space. I denote it like this, and this consists of continuous compactly supported functions now on E rather than G, and you want them to satisfy this T equivariance condition. So this is this action of T on E that I mentioned before. You want to be able to pull your elements of T out the front, basically. So this is a vector space under pointwise operations, and we're going to define a convolution and involution again. So first note that for each unit X, there's a Haar measure lambda X on this set GX. So this one's the morphisms with range X. This comes from the fact that G is a étale, and so it has a Haar system. And this is actually just counting measure. We define a convolution product as follows. So I'm going to use a different symbol for my convolution now because it depends on E. So F and G are 2 functions. And the idea again is that we want to if we take an epsilon in E, we want to decompose it into all possible decompositions and plug one piece into F and one into G. So I'm writing the decomposition as, I mean, this is epsilon zeta times zeta inverse gives you epsilon. I'm integrating over all possible zetas here that can compose with epsilon. So this means that the range of zeta is the source of epsilon. That's what this notation is. It's like one of these GX sets for E. And then I need to apply the corresponding measure, and I need my zeta to be in G for this. So that's why I'm applying Q. So this is.
Sorry, you said that the R measure was the counting measure.
Yeah, I'm going to convert this into a sum in a sec. Is that what you're getting
Okay.
at? Yeah. I just wanted to show the involution first. The involution's easy, but yeah, you can write this as a sum. So you can take any global section and it doesn't have to be continuous. So this is always going to exist. Just every element of G, you just take something in E that maps to it under Q. So P gamma for a given gamma. And you can write this as a sum. So here you're just summing over elements of G now. I mean, it's sort of not always nice because then you have this like P of gamma hanging around and you have to like keep writing things like, oh, it doesn't depend on the choice of P. So sometimes I like to just work with integrals, but yeah, often, I mean, usually sums are nicer and integrals are kind of ugly and scary. So yes, but anyway, you get a star algebra out of this and then you can complete it. So there's a full norm. And for this, you soup over all star representations of your star algebra, so pi, and you take the norm of pi of f, and you can complete your C-star algebra under this norm, and you get the full twisted groupoid C-star algebra. And I'm not really going to talk that much about this C-star algebra, but I just wanted to show it to you. So I'm going to talk about the reduced twisted groupoid C-star algebra. And for this one, it's similar, except you only soup over regular representations. So if you're only used to group C-star algebras, for groups, there's one regular representation. For groupoids, there's one for each unit in the unit space. So for each unit X, there's a representation pi X of this star algebra that we have on the following Hilbert space. So it's big L2 this is the morphisms in E with source X, except we don't just want all of big L2, we only want the T equivariant functions, right? So I denote this Hilbert space like this. And the way the representation works is, so like pi X of F would be a bounded linear operator on this Hilbert space. And we work this out, we apply it to a G by just using convolution as defined earlier. So these are our regular representations. And as I mentioned, we get a reduced norm by, in a similar fashion to the full norm, but now we're only souping over the regular representations. And the relationship between these two C-star algebras is that if G is amenable, then the full and reduced C-star algebras are isomorphic. And for groups, this is an if and only if result, but for groupoids, it's not. So there's an example due to Rufus Willett, even in the non-twisted groupoid setting, he's got this example of a non-amenable groupoid whose full and reduced non-twisted groupoid C-star algebras are the same. Yeah. So, okay, so before I get to the uniqueness theorem, there was a question?
One little question. So,
yeah.
E, is itself a groupoid?
Yes, not étale though.
Okay, but the C-star algebra of GE,
yep.
How does it relate to the C-star algebra of E?
E.
At the level of the star algebra, it looks like it is a sub thing.
Yeah, it is a sub thing.
Is it a sub algebra, or it sits inside? The operation is the same, or because use the P. I mean, I don't know.
Yeah, that's a very obvious question that I've never thought about before. But the first thing, I guess, is that you couldn't have this sum, right? Because it's not étale. E is not étale because of the T. It makes it not étale. I actually don't know the answer, but since if you actually want to know, I think I know a remark in a paper that mentions this, but I can't remember what it says. But I don't know at the moment. But no, it's a good question. I should know the answer to that. Yeah. So where was I? Okay, so this is just to formally say on this slide that if you have your twist and it comes from a 2 cocycle, then you do get the same C-star algebra. So suppose you've got a continuous global section, and then you can use that to build a 2 cocycle like I showed you before, so with this kind of property here. Then there's a star isomorphism of, so the star algebra I just showed you, and the one coming from, well, it's not sigma, it's the conjugate of sigma. And the way you build this map, I mean, it's sort of the first thing you would try, right? Like you've got functions here that are defined on E, but you want them to be defined on G. So you just compose them with your P, and that works to give you a star isomorphism. And it extends to isomorphisms of the full and reduced twisted groupoid C-star algebras. And then you can also say some extra things. So non-twisted groupoid C-star algebras can be thought of as like trivially twisted groupoid C-star algebras. So here your E is just G cross T with the expected multiplication in each coordinate. And then also, so I mentioned before that Q inverse of G0 is a trivial twist over G0. Also the C-star algebra is trivially twisted. So it actually just looks like C0 of G0.
One silly question.
Yeah.
You put in the proposition, you attribute it to Renault and to yourself, but I mean, there are 41 years from one to the other. I don't suppose you mean you prove the same thing 41 years later. Right? So what is it that you attribute to Renault, and what is it that
So Renault, I don't think had this notion of like a general twist. He just talked about if you start with a 2 cocycle, you can use it to build a twist. And so he doesn't kind of formally, I guess he doesn't formally do it in the same way. Like he doesn't start with a twist and then use it to build a 2 cocycle. He starts with a 2 cocycle and uses it to build a twist. But because of all this stuff about how there's a 1-to-1 correspondence, if you've got a continuous global section, it's essentially the same. It's just sort of not in this language. So I guess it's, I don't know, sometimes you want to reference a result that kind of looks more like exactly what you want it to say. So it's sort of, it's definitely due to Renault, but it's not obviously if you wanted it written in this form, I guess. But yes, I don't claim to have invented this 41 years later. Also, I don't know if he explicitly writes down the map in this form. I guess not, because he doesn't have a continuous global section in his initial data. Yeah, that's all I meant. Okay, so something, I guess, that comes up when you hear about twisted groupoid C-star algebras is these things called Cartan pairs. So Cartan pair is a pair AB of C-star algebras where B is a maximal abelian subalgebra of A that contains an approximate identity of A, and A is generated as a C-star algebra by the normalizers of B. I mean, don't worry about this definition because it won't come up again. There's a faithful conditional expectation of A onto B. So these 4 conditions give you what's called a Cartan pair, and we say that B is a Cartan subalgebra of A. And reduced twisted groupoid C-star algebras always have Cartan subalgebras. So this is Renault 2008 that says this. If you have a twist over G, then there's a faithful conditional expectation of the reduced twisted groupoid C-star algebra onto C0 of the unit space that extends restriction of functions. So, I mean, I'm using the identification from the previous slide because formally I'm restricting my functions to Q inverse of G0, but the associated C-star algebra I get is just C0 of G0. And then furthermore, C0 of G0 is a Cartan subalgebra of the reduced twisted groupoid C-star algebra. But this is actually an if and only if result. So if you start with a separable C-star algebra, A, it's going to have a Cartan subalgebra B if and only if it comes from a twist E over some effective Hausdorff étale groupoid G. So effective was this word I defined before that meant the interior of the isotropy of G is just the unit space. And then what's more is that this twist, like the pair consisting of the groupoid and the twist, is unique, and the B is going to be C0 of the unit space. And then this relates to classification as well, because Xin Li proved last year that if you've got a classifiable C-star algebra, which by this he means it's unital, separable, simple, nuclear, Jiangsu stable, and in the UCT class, then it will have a Cartan subalgebra. And so by Renault's result, every classifiable C-star algebra can be realized as a reduced twisted groupoid C-star algebra. And it's an open question as to whether the twist is needed to obtain all the classifiable C-star algebras. Like maybe you can just pick a different groupoid instead, and you don't need the twist anymore. I'm pretty sure that's open. But anyway, so I'm running out of time, so I'll move on to my uniqueness theorem. Actually, this is a kind of a preliminary result before I show you the uniqueness theorem. And yeah, once again, this one is definitely not, I wouldn't claim to have invented this result, but maybe in the form that I needed it. I proved it for what I needed it to do. So it says that there's a star homomorphism of, so this is the interior of the isotropy. It's a twist, and you get an associated groupoid C-star algebra, and I'm just trying to include it into the bigger twisted groupoid C-star algebra. And on the level of functions, I have functions on IE, and I'm just extending them to E by setting them to be 0 outside of the interior of the isotropy of E. So this gives you a star homomorphism, but it descends to an injective star homomorphism of the reduced twisted groupoid C-star algebras. And if your interior of your isotropy is amenable, then they'll both be injective. So then this map iota R, the injective one, is used in the uniqueness theorem. So, okay, so suppose you've got a twist and you've got a C-star algebra A, and then also a C-star homomorphism of the reduced twisted groupoid C-star algebra into A. Then this map is going to be injective if and only if the composition of it with this iota R is injective. So one of the directions is obvious. If psi is injective, then because iota R also is, then the composition will obviously be injective too. For the other direction, so you're starting with a map on this subgroupoid, like C-star algebra. And if you know it's injective, that tells you that the map on the bigger twisted groupoid C-star algebra is injective. And so this is what I was getting at before when I said that the interior of the isotropy is nice because its C-star algebra can tell you information about the bigger twisted groupoid C-star algebra.
This reminds me of the so-called Kunz-Krieger uniqueness theorem. Does it specialize to it?
I think okay, I do know that for non-twisted groupoid C-star algebras, they call this the Kunz-Krieger uniqueness theorem if you replace IG with the unit space. I think they call that the Kunz-Krieger uniqueness theorem. I suppose this is a generalization of.
I only know it for graph algebras.
But they have the same name for groupoids because of the graph one. Yeah. I think so. I nearly called this a Kunz-Krieger uniqueness theorem, but I wasn't quite sure. So maybe it's definitely close. Yeah. I'm sure the ideas are inspired by it. Yeah. So I should say this was proved already in the non-twisted setting, and I just proved it in the twisted setting.
Okay. So, but the twisted setting includes the non-twisted setting, and the non-twisted setting includes the original Kunz-Krieger.
Yeah, of course. Yeah. Okay. Yeah. So the interior of the isotropy, the C-star algebra tells you things about the bigger twisted groupoid C-star algebra. And also on the level of the isotropy groups, which are discrete groups. So you have like a discrete group twisted C-star algebra. You can get information about the bigger one. So I'm going to talk a bit about the proof. And the first thing I had to do for the proof was prove some result about state extensions, actually, of just C-star algebras in general. So this is just a technical definition to begin with. suppose you've got a state phi on a C-star algebra B that's contained in A, then it satisfies this condition. So we say A is B compressible modulo phi if for each A and each epsilon, there exists a B and a C and B such that this compression condition is satisfied. So if you compress A by B, you can get it within epsilon of C. And then so the B has to be positive in norm 1, and then this is how it depends on phi. It just means that the magnitude of phi B is 1. So here's the theorem. If you have a state of B, it'll extend to A if the state satisfies this compressibility condition. And the key part is that it's going to extend uniquely. I mean, the state will always extend. Compressibility tells you that phi has a unique state extension. And if you start with a pure state, then the extension will be pure as well. So I've got here I was a bit more precise about what my contribution was. So Joel Anderson in 1979 proved this for unital C-star algebras. It was believed for non-unital C-star algebras and like treated as fact, but I couldn't find it in the literature. But I mean, twisted groupoid C-star algebras are usually not unital. So they proved this for non-unital C-star algebras. And when I say I proved it, I mean, I'm sure somebody else has proved it in their life, but I wrote it down because I couldn't find it anywhere. So it's in my paper if you want it, but let me know if you already knew about it elsewhere. So yes, so anyway, so why this result? Well, here's a sketch of the proof of the uniqueness theorem. So I'm focusing on, what just happened? I'm focusing on this direction of if you start with this map being injective, then psi will be injective, right? Okay, so one implication is trivial. Suppose that psi composed with iota r is injective. We want to show that psi is injective. The first thing we do is use this result coming from this five author paper, and this is the paper that proved the uniqueness theorem for non-twisted groupoid C-star algebras. So they first show that this collection of units is dense. And so this is the collection where you look at, so for an X, you look at the isotropy group and then the interior of the isotropy group. And depending on the topology, these may or may not coincide, but they at least coincide for kind of almost all elements of the unit space. And then for each element X in that group, or that collection, sorry, you look at the collection of pure states of the isotropy algebra that factor through the corresponding twisted group C-star algebra. Remember, these are discrete groups. And you can show that they all satisfy the compressibility condition from before, where your A, the biggest C-star algebra, is the whole twisted groupoid C-star algebra. And so by the unique state extension theorem, all the states extend to a pure state of the bigger twisted groupoid C-star algebra. So you do this for all states in all of the SX sets. And then these authors, so I mean, they really did a lot of the work. They showed that this is just sort of a general C-star result. Like to see that psi is injective, it suffices to, so for each of these pure states up here, they have an associated GNS representation, and it suffices to show that the direct sum of those is faithful on your C-star algebra. So the hypotheses of this theorem, by the way, are that this XG set is dense, and also that all of the states have unique extensions. So that's why I needed to prove that bit. And then anyway, so then you just want to show that this direct sum is faithful, and it's just some pages of messy calculations, so I won't show them to you, but some of the things you use are the faithfulness of this conditional expectation that I mentioned before that extends restriction of functions. And you also explicitly use the compressibility condition that the states satisfy. So it's not just used to give you the unique extensions, it's also used to, the actual definition of compressibility appears in this. And anyway, then you get the result. So in my last couple of minutes, do I have a couple of minutes or should I just stop? I'm not sure. I mean, this is a natural place to stop, but I only have 2 slides. So what should I do?
A couple of minutes is fine.
Yeah, okay. So I just wanted to talk about simplicity. There's a corollary of the uniqueness theorem. I'll just show you a definition first. So we've seen G is effective if the interior of the isotropy is the unit space. And now we're going to say that G is minimal if for each unit X, you look at this set. So this is source inverse of X. So all the morphisms coming out of X, look at all their possible ranges, and that set is dense in the unit space. So it's like saying starting from an X, you can get almost anywhere else. So now this corollary, this is for effective Hausdorff étale groupoids. So what it says is that the C-star algebra, the reduced twisted groupoid C-star algebra, is simple if and only if the groupoid is minimal. So, I mean, I'll make a few comments about this. I mean, the first thing to note, the first thing I should say is this result was already believed, and I just happened to notice that it fell out as a corollary, so I wrote it down. But I think it's surely a corollary of other people's results. Like, I know Ralph Meyer has this, I think. Yeah, and Bartosz Krasniewski, I think, City's boss. Like, I know that it falls from things of other people as well. But anyway, it's only for effective groupoids, and I mean, the simplicity characterization doesn't even involve the twist. So somehow effectiveness is killing the effect of the twist. And I mean, what happens if you lose this effectiveness condition? Well, I mean, what happens in the case of non-twisted groupoid C-star algebras is the following. So in 2014, there's this result that says that for an amenable Hausdorff étale groupoid, the non-twisted groupoid C-star algebra is simple if and only if the groupoid is minimal and effective. Here I've just written the non-twisted groupoid C-star algebra as a trivially twisted one. So your E there is G cross T. But what I was going to try and convince you of is that this result, if I tried to apply it to actual proper twisted groupoid C-star algebras, would no longer hold. So I'm going to show you a counterexample on the next slide. So I'm going to take as my groupoid Z2, so pairs of integers. So it's an abelian group under addition. And so it's amenable, and it's not effective because groups, like non-trivial discrete groups, are never effective because they consist entirely of isotropy, not just the unit space. So they're not effective. So if they're not effective, then the associated reduced groupoid C-star algebra is not simple. Okay, so this is not simple, even though Z2 is minimal. So, I mean, here you've got a minimal groupoid, and then you get a simple C-star algebra. But that's not what's happening here because we didn't even start with the hypothesis of being effective. Okay, so that's what's happening there. Now I'm going to twist it. So introduce a rational number theta and build this 2 cocycle. So I'm taking 2 pairs of integers. And I mean, okay, I just wrote down the formula. You could check that it satisfies the conditions of being a 2 cocycle. So it's normalized and satisfies the 2 cocycle identity. But the point is that the associated twisted groupoid C-star algebra is just the irrational rotation algebra, and that's simple. So somehow,
you twist only on the left, right? So M and Q, no, so only on, only on the middle.
Yeah.
In the middle, okay.
Yeah, but it still involves each term. So it's, I mean, yeah. So I mean, you've changed the multiplication somehow and you've suddenly got a simple C-star algebra, even though you started with a non-effective groupoid. So you've broken this result. So it doesn't work for twisted groupoid C-star algebras. You need something more general. I believe you can construct the irrational rotation algebra without using a twist, but then it would come from a different groupoid, which I guess would be effective and minimal. Anyway, so this is the open question I wanted to leave on. Like, can we characterize simplicity or even describe the ideal structure, more kind of optimistically, of twisted C-star algebras of non-effective Hausdorff étale groupoids in general, or maybe drop Hausdorff or étale even. And so I say this is an open question, but the question of simplicity has been answered by me and Nathan Brownlow and Aidan Sims just recently for a certain class of groupoids called Dyakonov-Renault groupoids. So this is the class that the groupoids of directed graphs and topological Craig graphs and things belong to, but it's a more general class because it just comes from, you start with like an action of n to the k on some locally compact Hausdorff space by local homeomorphisms. And we just dealt with these groupoids these are amenable, actually, not necessarily minimal or effective. And we just dealt with 2 cocycles for our twists. And we got a simplicity characterization that involves the twists explicitly, because we built some action called the spectral action. And we got something like the C-star algebra is simple if and only if the spectral action is minimal. But anyway, for more general groupoids, this is not known. And I mean, you can describe the ideal structure of non-twisted groupoid C-star algebras. There's like a one-to-one correspondence between open invariant subsets of the unit space with the ideals, but not for twisted groupoid C-star algebras. So yes, I believe that's still open. Yeah. So I mean, here are my references. This is number 2 is the one that the talk was based on, and number 3 is about these Renault groupoids. And I mean, there's a bunch more. Yeah, I recommend Aidenson's notes for learning about groupoids. And also, I mean, I tried to put some nice background in my paper as well, actually, for twists. So yeah. Anyway, thank you. I'll stop there.
Thank you. Very nice talk. Are there any questions from the audience before I bombard Becky with questions?
Yeah, I had a question.
Yeah.
Becky, could you go back to the slide where you define this compressibility for these states?
Yes.
I really like the talk, by the way. I meant to say that before I asked the question, but
Oh, that's okay. I assumed you liked it because you came last week to when I gave this talk elsewhere.
Yeah, but I may have been a little tired in last week, so I'm not sure I heard the whole thing. So this, and I'm sure like Ralph may have talked about this with you at some point, but this B compressibility condition, or modulo 5, looks a lot like a condition that he and Bartosz Kwasniewski use called aperiodicity.
Yeah, so Bartosz told me about this. I think what he was saying was that you could end up using like the proof technique to get something about what are these intermediate C-star algebras?
Yeah,
which are these ones that sit in between the full and reduced.
Yeah, so this aperiodicity condition gives you detection of ideals in intermediate subalgebras. So if you have B sitting inside of A and then some C sitting in between, there's no ideals that are in C that A doesn't, or that the subalgebra doesn't detect.
Yeah, okay, so you could get like a uniqueness theorem for not just the interior of the isotropy, but like these intermediate C-star algebras?
Kinda. Sometimes like a lot of them come from like intermediate groupoids, but not all of them necessarily come from intermediate groupoids if you do this in a groupoid setting. But my question is, do you know whether this B compressibility is stronger or weaker or relates in any way to aperiodicity?
I haven't looked into the relationship. Bartosz sent me an email after he told me this last week, and it's something I plan to look into, but I didn't. I didn't do it yet.
That's fair.
Yeah.
I mean, if you've only had a week to look at it, and I'm sure you've been busy, so.
Yeah. So for the other people, there was this conference in Copenhagen that Jono and I were both at, and I gave this talk, but it was in like a 20-minute, 25-minute format. So yeah, it was a bit different.
Great. Thanks very much.
Are there any further questions? I wanted to ask, in this proof that you showed us, that so you cited somebody's result that so this X upper G was dense. But then when later on when you talked about simplicity, this GXX was just had one element. I mean, the what was it? Effectivity hypothesis is pretty much like the contrary, right?
Yeah. I think that's because that's an equivalent characterization of being effective, which is that the singleton X equals the interior of like the isotropy group.
Yeah, but what was it? Obviously I didn't. I'm not so familiar. I mean, I've read about groupoids and groupoid C-star algebras, but I'm not so acquainted with these things. But what struck me was that you made a proof in which you used a hypothesis or something or some result that said that for almost every point, the isotropy group is discrete because it coincides with the interior. But then you apply this as a corollary in a situation where it was just the opposite, because the minimality said like the contrary. So I mean, there is some logic there that I must be getting wrong.
I mean, so I mean, these are always both discrete. When your groupoid's effective, this is always just a singleton. So what's the issue with minimality? Because minimality is about, like, if you start from an X, you can get almost anywhere else.
Right, no, minimality with effectivity.
Effectivity. I
Yeah,
mean,
so effectivity will tell you that all of these have one element, right?
yeah, and I mean that.
So
well, for a dense set of points, all of these groups have one element. That's just an equivalent notion of effectiveness.
yeah.
I mean, okay, I think maybe the problem is this doesn't look like a very interesting corollary, is because of the effectiveness hypothesis. Is that kind of your point? Because I mean, I agree. Like, this is, I mean, it doesn't even involve the twist. I think my point here was that effectiveness kind of kills anything interesting that's going on. Yeah. I would not claim that this is an exciting corollary. It's just something that falls out. Yeah.
And from the point of view of, so we know that from this theorem of Lee that you showed earlier, that an algebra, the sister algebra that has a Cartan subalgebra is one of these, right?
Yeah. So,
for example, this insectivity theorem, what does it say in terms of without mentioning the twisted groupoids? Okay, so I have an algebra and I have a Cartan subalgebra. Then, I mean, does it say something like a star homomorphism that goes from the algebra to some other algebra is injective if and only if it is so in the Cartan subalgebra, or
right, okay,
something like that?
Okay, so you're not really talking, because I mean, with the Lee result, you're starting with a simple C-star algebra, so that's sort of, you've already said it's simple. So you're talking more about the Renault result and how to phrase the uniqueness theorem in terms of the original A and the B. Is that your question? Yeah. No, that's a good point. I haven't actually thought about it. I
mean, yeah, in the twisted setting, yeah.
Yeah, I mean, the Renault result doesn't even say anything about the interior of the isotropy, so I don't actually know what that looks like in terms of the A and the B. Yeah, but that's kind of a good question, because then, right? Because then you could you don't actually need to find out what the groupoid is to have a uniqueness theorem, I suppose. Like, maybe if the groupoid was kind of ugly, you might not want to introduce it. But yeah, no, thank you. That's a good comment, but I don't know the answer.
Just one little thing. The fact that algebras that are unital, separable, simple, nuclear, and C-stable, and in the UCT class are called classifiable, tends to give one the idea that those that are not in that class are not classifiable.
Yeah.
Right? So is there, I mean, C-stability includes, so I mean, I single out C-stability as, I hadn't, I mean, I know, I mean, people in Münster and other places have worked a lot on C stability, but I didn't know that, that was a necessary condition for algebras to be classifiable. Is there some logic theorem that says that, I don't know, that you cannot classify those that are not in this class or something like that?
So there's results of like many people that says if you have C algebras in this class, then they're classified by their Elliott invariant, right? Like K-theory and traces.
Yeah.
I know that, so firstly, the reason I use the word classifiable is because Shinley's paper is literally called like every simple classifiable C algebra has a Cartan subalgebra. And then he says by classifiable, I mean these adjectives. So that's why I used it.
So this will be classified.
Yeah. And then he has some results in different settings. Like he's like, suppose, I think he picks out some of the adjectives and says what you get in those cases. I can't remember precisely what he does. But I mean, yeah, okay. I'm definitely not part of this. I mean, I'm quite new to Munster, so I'm definitely not one of these big classification people. But I asked around and said, is it reasonable to call this class classifiable? And people were kind of like, yeah, you just sort of say it with confidence and then, yeah, it's agreed upon. But I have heard other people refer to this as the like classifiable C algebras, but I guess the classifiable C algebras is like a growing class, right? Like that's the goal, to classify C algebras. So I guess eventually you would remove some of these adjectives, but then maybe you wouldn't get a Cartan subalgebra.
Okay, thank you.
I don't really know a good answer to your question.
Oh, okay. So we stop the recording.